This lesson will cover Unit 2, Acquisition 4. We're talking about periodic trends down a group. So as a reminder, when we're talking about groups, we're talking about the vertical columns. So what happens to reactivity, atomic radii, ionization energy as we go down group 2, for example? So last lecture when we talked about periods, we used Z. When we are looking at groups, the reasoning that we want to reference is Coulomb's law. So Coulomb's law states the force of attraction between two oppositely charged particles is directly proportional to the magnitude of the charges. So directly means the same. So if the magnitude of the charge increases, the force also increases. As one goes up, the other goes up as well. So the force of attraction between our oppositely charged particles is directly proportional to the magnitude and inversely proportional to the distance. Between the charges. So what the second part of this means, inverse just means opposite. So as the distance increases, the force would decrease. If distance goes up, force goes down. So how does that help us explain trends as we go down a group? So let's look at lithium versus sodium. So lithium is in period 2. It has 2 energy levels, and it's in group 1, so it has 1 valence electron. If we go down the group to sodium, sodium is in the 3rd period. So it has 3 energy levels. So let's look at the second part of this. Coulomb's law says the force of attraction between our positively charged nucleus and those negatively charged electrons is inversely proportional to the distance. So the distance between that positively charged nucleus and my negatively charged electron in lithium is going to be less than the distance between sodium's positively charged nucleus and its negatively charged valence electron. So as that distance increases, the force of attraction decreases. That will be the important trend to remember as we talk about our various properties. So up first, atomic radii increases down a group, which we can see with our group 1 metals. The atomic radius of sodium is greater than the atomic radius of lithium. The reason why As we go down a group, the valence electrons are farther from the nucleus, so the attraction is weaker. Since that attraction is weaker, the electrons aren't pulled in as closely. So if we have a stronger attraction between our nucleus and the valence electrons, those electrons get pulled in tighter, meaning the atomic radius is going to go down. As those electrons get farther away, the attraction gets weaker, meaning those electrons aren't pulled in as tightly, so we're going to see a larger distance. So let's do a few examples for atomic radii. Determine which is larger. So A, potassium versus rubidium. B, chlorine versus fluorine. C, this one might be a little bit trickier, magnesium versus potassium. Alright, so A, this one should be easy, straightforward. We know that the trend is atomic radii increases as we go down a group. So rubidium is farther down the group than potassium, so rubidium would be larger. Chlorine versus fluorine. Again, atomic radius increases as we go down the group. So chlorine would be larger than fluorine. The reason why I said C might be a little bit trickier because we have to take into account both properties. So magnesium and potassium not only are in different groups, but they're also in different periods. So remember the trend from our lecture on periodic trends across the period. We said elements are larger on the left. So potassium is to the left of magnesium, and it is also further down. So atomic radius increases to the left, and it also increases as we go down. So according to both trends, potassium should be larger. The next trend we are going to look at is reactivity. Reactivity of metals increases down a group. Reactivities of metals increases down a group. Reason why? Again, we're going back to Coulomb's law. The valence electrons are farther from the nucleus, so the attraction is weaker. Well, how does that affect reactivity? So the weaker the attraction, the easier it is to lose electrons, and the easier it is to lose electrons, the more reactive it will be. So we can go back to those Bohr diagrams of lithium and sodium. Since sodium's valence electrons are in a farther energy level, as that distance increases, attraction decreases. As that force decreases, it's easier to lose electrons. Sodium would be more reactive than lithium because it's easier for sodium to lose its electron. the easier it loses its electron, the more reactive it's going to be. So let's rank some metals in order of increasing reactivity. Let's say you had sodium, lithium, rubidium, and potassium. So these are all group 1 metals, and we're going to rank them in order of increasing reactivity. So we said the trend is that reactivity increases as you go down a group. Lithium is at the top of the group and reactivity increases as we go down. So therefore lithium would be the least reactive, followed by sodium, followed by potassium, and rubidium would be the most reactive. Last trend for today is we are going to talk about ionization energy. So remember, ionization energy is the energy that it takes to remove one electron. Our trend is that ionization energy decreases down a group. Ionization energy decreases down a group. So we know that as we go down a group, the valence electrons are farther from the nucleus, so the attraction is weaker. So how does that affect ionization energy? Well, as we go down the group, we have a weaker attraction. Well, if that attraction is weaker, it's going to take less energy to remove an electron. So in the case of lithium, that electron that's negatively charged is pretty close, relatively, to our positively charged nucleus. So that attraction is going to be pretty strong, which means it's going to take a lot of energy to remove that electron. That attraction is going to be weaker in sodium because the distance increases. If the attraction is weaker, it's easier to lose that electron. So ionization energy is the energy it takes to remove an electron. The weaker the attraction, the easier it is to remove that electron. So last practice problem, we are going to rank in order of increasing ionization energy. So again, for this one, we need to put a few of our trends together. We need to look at trends within a group and also within a period. So we're looking at germanium, which is right here, indium, which is right here, and we're looking at cesium, which is right here. So our overall trend for ionization energy is it increases up and to the right. So we just said that our trend was ionization energy increases down a group, or we could say it increases as we go up a group. So elements as we go up our groups are going to have a greater ionization energy. Last lecture when we talked about ionization energy, we said ionization energy increases as we go across a period. So it increases to the right and it increases as we go up. So knowing that, we should be able to rank our 3 elements in order of increasing ionization energy. Cesium would have the lowest, followed by indium. Germanium would have the greatest ionization energy.